Thank you all so much for coming. I know how far many of you traveled, all the way from Philadelphia and places as far away as that. You managed to make it here. It's a remarkable achievement, Dan, and winning. In any case, the title of my slide, I think, sums up what I want to speak about. It's the 25-year mission that we're about to embark upon. And that mission is to barcode the planet. And I want to begin, before looking to the future, looking at the past. And I can't tell you, as you look at the screen, you may think it's a little pale. We've gone through great efforts to get this screen up. We had to tear down a big plasma screen that was very bright, but had lots of bezels across it. We couldn't stand it. So this happened at 10:30. We were praying for darkness and rain today, but damn it, the sun's out a bit. Anyway, I think you're going to be able to see the things. They may not just not pop quite as much. In any case, this is the group that assembled here at the University of Guelph in 2007. Some of them are still alive. Yeah, I'm happy I'm one of them. In any case, this was the group that came together and asked the question, was it feasible to develop a DNA-based identification system for the planet? Should we try and do this? And the decision within just 2 days was we should. We came up with a name for the project, the International Barcode of Life Project. So as Jonathan indicated, it was a project when it was initially conceived. Aside from a name, we came up with some goals during that meeting. And one of the big goals was to try and do something within a 5-year time period. So we set a time frame, we set a production target, we wanted to deliver 500,000 sequences for 500,000 species in that period, and we tried to estimate what it might cost, and we thought it would cost about $100 million. And for biodiversity scientists, that seemed like a substantial sum. That first meeting led to meetings around the world, and this is the meeting in Leiden in the fall of 2007, so just slightly after that meeting in Guelph, where Europe came together and said, shall we think about getting involved in this project? And there was much positive attitude there. This is a meeting in Beijing at the Chinese Academy of Sciences, where they reinforced it, and we were so pleased to see that big banner up there, 40 feet long, International Barcode of Life. We thought this is pretty spectacular. We came back the next day and there was a different banner up. Oh well, they make beautiful banners, so I still have it. Here's another meeting in India. Anyway, there's a whole cascade of meetings around the world to try and build the momentum, the research team, the alliance, and to try and secure the funding. And that took 3 years. So this is now 2010, 3.5 years after that first meeting in Toronto and in Nagoya, at the CBD meeting in Nagoya in 2010, the individuals who participated in the launch meeting of iBOL 1. And we ran a barcode of the Castor canadensis, the Canadian beaver, up the CN Tower. We'll see the CN Tower tonight from the water. How did iBOL do? Well, that's the barcode coverage in 2010, and you can see the number of sequence records ranging, and so we want to paint the world, obviously, in magenta, that kind of color, looking a bit weak right there, and this is in 2015. So the world is starting to go magenta, but there's an awful lot of places that need an awful lot of more analysis, and but the fact remains that in August of 2015, we could say that we had achieved the target. And I think for much of the period that that project was underway, I didn't think we were going to do it. But we did it, and it was sort of time to celebrate. But on the other hand, it wasn't time to celebrate, because I just left that meeting just thinking about this. That iBOL had done, substantial work, but it had managed to register only 5% of the multicellular species on our planet. So there was an awful lot of work that needed to be done. And in fact, at the meeting, at the conference that was held here in August 2015, I talked about this project. I introduced this concept of a mission for planetary biodiversity, what it would take to complete the inventory of life on our planet, and why we'd want to do it. I'm not that fascinated with just completing the inventory. I'm much more fascinated with using that inventory to help manage life on our planet. So this was the 3 key goals for the Planetary Biodiversity Mission. The first was to complete the census of species. The work that we in the biodiversity science community have been doing for 260 years now, to understand life on our planet. And in the course of that, of course, we're gathering up all these organisms, we're extracting DNA, we're building a genomic repository, and the idea was that Barcode of Life would not do that, but Barcode of Life would create this asset, the global library of life, this repository, and other people that can come in and sequence those will be delighted to see that done. And the Earth Biogenome Project is, in fact, proposing to do just that for each at least of the described species. The other thing, and actually I see this as the driving mission behind all of this work. Why do you build a library? It's so you can develop a global biosurveillance system that makes it possible to protect biodiversity on the planet. I don't know how you protect inventory of life on the planet if you don't know where it is and how many different items you're trying to protect. So that was the mission. And there were a couple of problems. One was the uncertainty. The uncertainty in how many species are out there. We've been working at this for a long time, but we don't know. Is it 10 million? Is it 20 million? It could be many more than 20 million. So that's a big uncertainty. If you're, when we launched objects towards the moon, we knew how far away it was precisely. You can engineer those kind of a solution. We don't know that with species diversity on our planet. However, we did know enough that it wasn't going to be cheap. There were certainly, best estimates, at least 10 million species, and it was really easy to see how you could spend at least $1 billion to carry out these projects described. And if 100 million is scary, $1 billion is even scarier. And so I hit the pause button. I might still be in pause mode, except for Michelle. Is she here? Is she awake? Where is she? Where's Michelle? Why can't I see her? There she is. How could I not see her? And this is what happened. This is Kruger National Park, a Rondeville. And there are pictures here without anyone in the Rondeville because we had everyone leave their iPhones at the door. No communication devices were allowed in the building, so there would be no recording of the conversations that happened there. In any case, let me reveal what happened, and that is that we considered 2 possibilities. That iBOL would be iBOL, and we would write a paper that declared its grand success and it had achieved its 500,000 species. And let's go away and party. And that seemed like a great option. Unfortunately, the countervailing view was that really we should keep this thing going. We should extend iBOL, and we should press forward towards the Planetary Biodiversity Mission. We were drunk at the time. Unfortunately, we had sobered up 2 days later, and the views hadn't changed. Yikes. Big implication for me, there went my retirement. I had such nice retirement plans. Oh, well, okay. However, I hesitated. Conversations in Africa, you need to come home and think about them. And I really thought about, could we achieve major goals? Can we raise the funds? Were you guys still keen to proceed? So a number of you got emails, and I think I was looking for an escape. I was sort of hoping that, yeah, we've sobered up, back home, yeah, we don't think it's a good idea, write that first paper and shut this thing down. No, unfortunately you wrote and said, yes, we must go forward with iBOL 2. Okay, we're ready to roll. It seemed important to think about the past and say, did we learn anything when we did iBOL 1? This is the wonderful tricolor iBOL map. The world is painted in these very vivid colors. 25 nations involved, 25 nations, each nation developing, even little New Zealand down here, developing a national network with researchers contributing to the iBOL project, nations contributing at different levels, regional nodes, like here's a classic regional node here, Argentina. Argentina, where the desire was for regional nodes was not just work in your own country, help countries around you understand barcoding. And Argentina's now run a training course for 10 years, and I think, Pablo, were there not 80-some people at, Pablo, were there not 80 people at this course? Yeah, which is phenomenal. So Argentina's been functioning in this mode. There were also plans for 4 central nodes, Canada, United States, Europe, and China, that would do the heavy lifting, that would lead the informatics program, and would also create big core sequencing facilities. That was the plan. Didn't unfold that way. Turned out there was only one core facility that was developed, the one here, but happily it was able to increase its production to meet the needs of the project. I'm not saying Europe didn't do anything, or the States. Obviously they were deeply involved, and China too. China hosted meetings, very active participation by many European nations, but we decided it was just most cost effective to have a single core facility and channel the work through their economy of scale. So that was iBOL 1 in a nutshell. Complex plan, way too complex, demanded coordination for funders that I now believe it's really, really difficult to get. In biodiversity science, all nations to march forward with a singular plan. That's something we need to try and change in the longer term, because it's what the astronomy community has, that kind of international capacity to mobilize. The other problem with iBOL 1 was just the way we approached it. We went to nations and tried to secure signatures from as many organizations as possible. Here's the top part of one MOU for iBOL 1. For Australia, the Australian Museum signed, the New South Wales Department of Primary Industries, the Planet Gardens Trust, etc. When you get a whole bunch of organizations to sign a piece of paper like that, and the cost to participate is the ink that you wrote your name with, it's amazing how many people you can get to sign. But it's also amazing how little responsibility people feel for delivering the product. Just everyone says, okay, someone else is going to do it. And on the other hand, you don't get much credit. If something miraculous happens in Australia, the freeloaders sort of drift along in the backwash of the institution that's leading. So those are the lessons. And this is iBOL 2. It's paler colors. First of all, it's not the in your eye, which we're a little more subtle, it's a little softer. We've got only 2 colors, but you can't just become green color. You can't become a member by signing on a piece of paper, as you know. And I'm really grateful that you've gone to your administrations and you've raised the membership fees to join iBOL 2, because I think that has important benefits. People take it more seriously if you're a formal member in something like this. There is a single person in each nation who has responsibility for delivery, and that's you people. It's not some diffuse entity. It's a person who says, I'm going to try and help this project mobilize. Your institution is behind you. They're paying the membership fee. So we now have an institution. And we're not saying don't partner up with people in your nation, but we're saying there is a sense of responsibility. You've joined this enterprise, you're going to do something to make it a success. So that's a little bit about, oh, sorry, I'm going to back right off there. I should have talked about the associate members. What exactly is an associate member nation? And what happened as people started to hear about the potential activation of the second phase of iBOL, I started to get letters from nations saying, we would really like to participate in this, but it's quite difficult for us in Nepal or us in Armenia to raise that membership fee, especially in the short time available. And I just thought it would be a real pity to decline interested researchers who would want to join us for the sake of a membership fee. And so I'm proposing, and this is something for us to consider collectively, is if we want to just go with a green class, or if we want to think about encouraging participation by associate member nations who would be expected to contribute. Not a membership fee, but with in-kind resources, specimens collected in their nation that could help us to achieve our goal. So that's a thought. I think it's tomorrow when we come back in our discussion session, that's one thing I want to revisit, how you feel about associate member nations and how we might police that people actually do contribute and don't show themselves an associate member and then nothing happens after, again, signing an MOU that I'm an associate, that we're an associate member. This is a structural diagram. Michelle, you'll hear from Michelle tomorrow. She's done a magnificent job to develop the first phase of the website for iBOL 2 that we'll get to see in a little more detail tomorrow. This is the structural diagram. There'll be an annual membership meeting, and the next meeting of this group will be in Trondheim at the next International Barcode of Life meeting. Sometimes we just stapled it into the meeting program. That didn't really work. That's another lesson learned from iBOL 1. You need to have time for discussions. So we'll take at least a day in advance of the meeting or a day and a half in advance of the meeting to make sure that we actually can dedicate time. The Scientific Steering Committee, what are you responsible for? The conferences. Every 2 years we have a conference. We need to decide on the location. We know what the next conference is, but where will the conference in 2021 be held? Responsible for growing out the reference library, responsible for thinking about this global biosurveillance system, how we get there, and then finally fostering applications of DNA barcoding, because society is often more hungry to support science when they can see the outcome. A board of directors, and we have two of the members of the board of directors here today, Jonathan Coddington at the back, Daniel Jansen, and we really appreciate your contribution to the success of this project. Wolfgang Bagley is also involved, and sadly John LaSalle was going to be on the board of directors and was killed in a car crash this year. So we're still regrouping and thinking about Australia, but I missed y'all. Collaboration. The board of directors is involved in fostering collaboration, looking at the strategies that we accept in a critical way, we develop, managing the project in a sense, and also looking at the financials. It's not we're going to have, I don't expect vast cash flow through the corporation that was founded in 2008, but there will be cash flow associated with the membership fees and likely other contributions. So we need to have a fiduciary body that looks at that and stamps and says the corporation is operating in an open and transparent fashion. So that's perhaps enough about organization, and I think it's all open for discussion. If you've got other ideas and thoughts, tomorrow afternoon, we'll spend some time on it. What are our scientific goals? I mean, this is really, what drives this is a science project, and we're very interested in deliverables. And so this is a little Moonshot cartoon. We're aiming towards a fully barcode parameterized world, a magenta world, and how do you go magenta from where we are today? Because that's the world today, at least staring in at planet Earth. And I'm pretty sure it's going to be a three-phase project. So iBOL 1 we've done. That was a launch module. It drove up barcode coverage for 500,000 species. That was really the big mission. iBOL 2 is the booster module, a 7-year booster. This was a 5-year launch module. And what is the goal? Well, the goal might be try to raise that barcode coverage to 1.5 million species. And we also need to think about biosurveillance, not just building the library, but beginning to lay the foundation. This project laid the foundation for building out the sensitive species. We need biosurveillance, and then we launched the 20-year module that the PBM that will deliver 20 million species, perhaps, if there are 20 million or more, barcode records for those, and launch the global biosurveillance program. So I thought about these, and I thought about this one in particular, and I just couldn't get excited. It just, 1.5 million species. Okay, that's a big number. I'm not sure we can make it, but I didn't find it exciting enough. So I thought, what the hell? Let's go for 2.5 million. Oh, God. Why do I do that? You may be right. Come on, Paul, get serious. Let's go. Let's drop back to 1.5 million species. That's going to be stressful enough. I think it's important. We're talking about 2025. I think it's really important that we signal in 2025 that we're not lagging behind Linnaean taxonomy by 500,000 species. Because by 2025, there will be 2 million Linnaean species described. I would like to press us past Linnaeus, show that we can transform the system. So how are we going to get there? And are we likely to get there? I don't like being involved in projects that fail. So this is what happened to barcode coverage, starting in 2004, passed through 2015, the 500,000 species, and we're now trajectorying toward, by the end of this year, 700,000 species. Okay, it's rising. 700,000 is not a bad number, but you'll see something nasty happening. The slope is declining. Since we took the pedal off the gas in 2015, we started sitting at, we're going to hit 700,000. But if you project this out to 2025, the number you hit is about 1.1 million species. So carry on doing what we're doing, and we're not even going to get close to what do you make the 1.5. So we need to do something different. Look, there are some botanists in the room. I feel sorry for you. There just aren't enough species, Pete, for us to, we can barcode every plant species in the world. I don't think we can hit the total. It's maybe 500,000 species. And we want the plants there. Every species record counts. And so we sure want the plants, and let's get as many plants barcoded as possible. But they're not going to take us above the Linnaean total. Fungi. Well, there are a lot of fungal species. The 5 million is pulled out of the air. No one has any real idea. Yvonne, I think you would agree that we don't know how many fungal species are on our planet. It's certainly millions. The one thing we do know so far is that not much work has been invested in barcoding fungi. We still need more work to parameterize the best approach to fungal barcoding, I would say. So we're not ready to really scale up and go crazy with fungi. What about animals? Well, there are lots of animal species, 15 million. So we know there are plenty of animals. We also know that we've got a program which is functioning very effectively. In terms of barcodes function very effectively. But here's the key problem. How do you barcode more species than have ever been described? Develop a new method to register species, of course. And what might that be? Well, this is the interesting pattern we've seen over the years as we began to look at the barcode index number system and sequence clusters in animal groups. If you look at the species counts for groups with really good taxonomy, and then you look at barcode clusters, there's this wonderful correspondence. They're effectively the same. Most species form a distinct sequence cluster. And Sajeevan and his team made use of that observation that we'd seen since the very earliest days of barcoding as a basis for the barcode index number system, that you basically go out anywhere, collect specimens, sequence them, and you can count the number of sequence clusters. And that's going to be basically a species count. But it went a little further. It didn't just count them, it named them in a non-traditional way with alphanumeric characters. But they've got names. And really now, if you're interested in animal diversity, you can go anywhere. You can collect specimens, you gather the barcode region, you analyze it with the PIN algorithm, and you get the number of species at that location. So the species counting has become automated, basically. And here you can see what comes out of that, a barcode index number. This is one of 560,000 on bold right now. Images, distributions that are sort of falling off here, images of more specimens. That's interesting. Where do we sit today in terms of the countries in this room? Number of sequences, number of bins, there's all the nations that are associate members and members. And Lebanon, I promise we're going to press you up to 50,000 before very long at all because of your great participation. I mean, these are the great, and that's where Jansen was a few years ago. He was down here actually, 2004. I think he had 3 records, but he did something to press him up from there. So that's where we stand right now. I find it really interesting. The relationship is so linear that we can't see Costa Rica sort of exploding out of the ranks, and Canada's up there right at the top. There are more species in Canada than Costa Rica, I'm sure. Them's fighting words. Okay, Linnaean species versus bins. This is the business of Linnaean taxonomy. You look at things really hard, a little pink thing is a human face. An emoji or whatever it is. This is what we do. We embed new species in the Linnaean higher taxonomic categories. We assign them a Linnaean name, a binomen. We pick a holotype, paratypes. We have other specimens at the time of description. These are fixed. Specimen collaterals, date, time, place, collection, so on and so on. Morphology, we take a look at that. We use that to diagnose characters. Often don't do molecular and do track synonymy, but it's a little painful sometimes. So here's a bin. At the moment, we use morphology to assign a bin to higher Linnaean categories. In the future, it will be automated, probably within the next couple of years. It gets an alphanumeric name, that's the bin. So that the species is named effectively. What don't we do? Well, there's no type material. Other specimens is dynamic and active. It keeps getting updated as you add new members to the bin. You've got this wonderful attribute of having dynamism in terms of collection dates, locales, collector. Images, we don't take a lot typically, just a couple, so they're pretty fixed. Here's another big gap. We don't identify diagnostic traits. The bin algorithm doesn't do that, either molecular or morphological. And then finally, we're not doing an active job of tracking synonymy. So that's where we stand today. What about getting rid of those differences between bins and Linnaean taxonomy? Let's augment the bin system and let's create a new way of describing species called GenoSpecies. So a GenoSpecies, by the time we launch it, it will be automated in terms of the placement within the higher taxonomic categories. There will be the bin alphanumeric, that's a species ID. Let's designate type material. Let's fix a holotype at the time that bin is encountered. That's the genotype for the GenoSpecies. Let's pick paragenotypes. They will be picked automatically. Other specimens, every time someone encounters another member of that GenoSpecies, its details will be dynamically incorporated. Ditto with specimen collaterals. What about diagnostic traits? Well, we're not going to get into using morphological diagnostic traits, but we can employ dynamically molecular traits. All of a sudden, this starts to look, and we can track synonymy in an automated fashion. All of a sudden, this starts to look an awful lot like a species description. And I propose this is the way we're going to blast through the Linnaean limit on species. Moving to GenoSpecies, not to replace Linnaeus. This is a platform that's very similar to Linnaeus and will keep describing species as time and opportunity and human effort permits. But we can't let the morphological demands slow things up. How many species will need to be analyzed? That's one of the big things. How much work? How expensive? I looked everywhere in the web and I could not find anywhere an Amazon biodiversity warehouse. Like, how cool would it be if we could just phone up Amazon, email Amazon, and ask for one specimen of each of those 20 million species? That would make our life easy. Can't do it. Got to go out and start collecting. And that's going to lead to oversampling. There's no way you can just encounter one individual of each species. You oversample. We have been sampling insects with your help. Many places around the planet, 1.8 million specimens have now been barcoded. And this is the trajectory. Specimens, bins, replace that with GenoSpecies. There's a linear pretty much linear, no surprise. We think there are 10 million insect species on the planet. We're going to have to do a lot more sampling to make this go nonlinear. But the important message is we're analyzing about 10 specimens for every new bin that we encounter. What does that mean? It means that we may have to analyze, let's suppose, that should not say, yes, that should. Let's suppose 20 million specimens is our goal for iBOL 2. If we're trying to pick up about another 2 million species, we're going to have $5 a specimen. It's going to cost us $100 million. And that number seems a little intimidating. That number suggests you really should work hard to reduce your analytical costs. Because we pressed real hard on Sanger technology and we couldn't drive costs down much below $5 a specimen. So we knew we had to look for something different. And again, he'll talk to you much more tomorrow about the SQL platform. But this third generation sequencer is quite a magnificent instrument. And here you can see the comparison between a Sanger sequence in black and the PacBio sequence. They're identical. So in contrast to some of the other next-gen platforms, these generate Sanger quality sequences for the reference barcode library. And the other amazing thing about them is this machine can run 10,000 specimens at a time. This is 9,120 specimens injected into this thing. And in 6 hours. So this little machine, with these little chips, if you turn it on, you can process 5 million specimen barcodes in a year. And just think about what that means in terms of species registration. One machine could potentially register 500,000 species in a single year. Global taxonomic community, past 2.6 centuries, an average of 6,500 species per year. Past decade, 15,000 species per year. Turn on one sequel and feed it specimens, and you will register 500,000 species. Amazing. How are we going to do that? How are we going to meet the goals of iBOL 2? And here's a little trajectory, starting next year, 2019, because that's when we're going to start. And here are the number of specimens that we need to analyze per year. 1.5 million, rising up to 4.5 million in the last year. And if we do that, we'll satisfy that need for 20 million specimens being analyzed. Who's going to do it? We're prepared to commit to the following trajectory. We're currently running about 1 million species. We will crank up production, and we will aim to drive it to 3 million specimens per year by 2022. We could keep cranking, but we'd much prefer this model, where we basically go static after that, and somewhere else on the planet picks this up. Chenxi, why not China? GD, why not India? Somewhere needs to create a second core facility that presses through specimens at this pace. Starts at 500K, goes to 1 million, then 1.5 million. We do that, 2 facilities. We then have a method to deliver the coverage that we need to satisfy iBOL 2. All of a sudden, the challenge, moving to SQL, we've collapsed the cost down to $20 million. From 100 to 20 million with just that platform change. Because I think I didn't show you, or talk about what I should have, is our cost next year, we're projecting $1.50 a specimen, and we're determined to drive the cost down to 50 cents a specimen. You collect a specimen, you get a barcode record, go through DNA extraction, PCR amplification, and sequencing for 50 cents a specimen. Evgeny has just gone pale. But Evgeny, you're going to do it. I don't know how you're going to do it, but you're going to do it, damn it.
Yeah, 2022, this is when they retire.
Yeah, that's right. Yeah. Yeah, well, I won't be retired. I plan to see it happen. So. There is one problem. Asking your help in what I call the Stop Dan movement. I mean, if we don't do something, Dan is going to take the entire capacity of our core facility here. and only run specimens from ACG or Costa Rica. There's no question about that. So I need help. And in particular, I need you to help collect specimens from different places around the world. And that we're trying to imprint you, like many of you are new, and it's like little goslings walking and they imprint on their parent. The idea is if you walk by that malaise trap often enough between here and there as we feed you, you will want to set up a malaise trap when you get home. If you do set up a malaise trap, you will collect about 30,000 specimens in a single year if you just put one of them in those. So that's how the Stop Ban movement is focused on everyone setting up a malaise trap in their backyard, and then we get 1 million specimens a year, not from the ACG. Fantastic idea. So, building out the reference library is going to do something very important in terms of PBM goals. We're going to be taking up the sensitive species in a very major way. Lots of DNA extracts are going to be gathered as a consequence of it. And it's the underpinning for this next step of protecting biodiversity. We need to work towards a global biosurveillance system. It begins with fragmenting the planet into a certain number of blocks, and I sort of like the idea of 1,000 blocks on land, and that gives you 3,000 blocks in the water. So here's South Africa, good-sized country. Turns out that when viewed in these blocks of 150,000 kilometers, it would have about 6 of them. 150,000 kilometers is a pretty big place. You could fit Costa Rica into it 5 times. So we're going to allow Dan to set up a few sampling stations in Costa Rica. You can have, divide each of these blocks into about 60. And imagine a sampling system in the center of every one of those spots. So that's sort of the thought in terms of a global design of a global biosurveillance program. Here in Canada, it's bigger than South Africa. We have 70 of these damn blocks. And this is the block that we sampled this year. Grid the province, go out, sample in every one of these grid squares, monitor biodiversity. This is what we did this year, 2019. The boreal, we have 15 ecozones in Canada, and the idea is we're going to march across Canada and up into the Arctic and do this intense biomonitoring across Canada. This is laying the foundation for a global biosurveillance system. Every one of those blocks is 1,000th of the land surface of our planet. In 2023, we will move away from turning on and off this biosurveillance. We will set up 500 places across Canada, or in our cities, in our agricultural fields, in our national parks, provincial reserves, and plan to monitor biodiversity in perpetuity. And we'll do it for a few $1 million a year, and we'll be analyzing at least 15 million specimens, the size of the Canadian National Insect Collection. And we'll be doing it every year for the future. This is like the way we measure weather. And Michelle, you're going to talk to us tomorrow about the wonderful work that you're doing in South Africa. This is starting to spool out in other places in important ways. And of course, it's all based on metabarcoding, taking large collection specimens, extracting DNA, amplify, and then bang it up against a reference library. We've been doing this kind of stuff. Last year, we took 1 million specimens, and we took a week of machine time and ran those 1 million specimens. And 250,000 were done as single samples, 750 as bulk. So those are big numbers. And that's all it took to do the single specimens, 28 chips on the sequel. We found 14,000 species, GenoSpecies, if you will. Did the same thing on another platform, the S5, for bulk samples, revealed 19,000 species. And here's the combined curve, 25,000 species in a week of machine time. And this is the thing I like particularly, and these are these 45 sites. And these are the species that were only collected at that particular site. These are the connections between sites. And this only shows 17 of the potential locales. Can you imagine how complicated this would be with 45? This is the beginning of a biosurveillance system for our planet. Okay. The elephant in the room. What is iBOL 2 going to cost? My best estimate, if we follow this path, is about $180 million. Someone could write a check before you leave the room, it would be much appreciated. $90 million is in kind. We need about $90 million in cash. And I'm not going to go through the breakdown, but this is our best estimate of what it will cost to do it. Have we got any funding for it? Right now in Canada, we have 15 million in place through 2024. We're working on applications for about another 12 million. So we know we're going to help this project advance, but we can't do it alone. We need to look at every possible source of money that surfaces anywhere on the planet. Everyone from Europe, Nicola. Last week, Biodiversity announced, I'm sure you know about it already, announced their new program. There's about 12 million euros up for grabs, looking at the relationship between biological diversity and animal, plant, or human health. We should be applying to that. Not us, because we can't apply, it's only European nations. The Gates Foundation just announced a search for tools and technology for broad-scale pest and disease surveillance. Not much money, $100,000 for the first thing, but a very fast review, and potentially, if we're successful, could be $1 million for the second phase. So, I mean, we need to go after every possible broadly opened agenda item, but we also need to approach foundations and we need to approach our national governments and not just wait for opportunities to rise. So that's what iBOL 2 is going to do. The long-term vision, of course, completing the planetary biodiversity mission. If I take stock today, I think we have the hardware in place, the technology today that will allow us to realize the goals of the PBM. And of course, it's going to keep evolving. The software, the BOLD, and the Embrace platforms are going to provide the informatics support we need to keep this project going, and we have a wonderful community of people around the planet who want to contribute to it. We're talking now about launching a project that runs for 7 years, from 2018 through 2025. Oh, it didn't change it. There you can see, oh my God. 2.5, get rid of that thought. 2.5 million species barcoded, and biosurveillance underway leading into this grand project, the PBM. Can we afford it? Of course. Humanity spends billions of dollars. I did use this slide a week or two ago in the Netherlands, so it was euros. We do spend billions of dollars, euros, whatever your favorite currency, to advance understanding of our world. Planetary Biodiversity Mission will cost about $500 million. The recent New Horizons flyby of Pluto was $700 million. My God. If humanity can find $700 million for a flyby of a very distant object, it's got to be able to find $500 million to protect life on this planet. So we're living in the Anthropocene. There's urgency to the work that we're talking about doing. Much life on our planet is in peril. If you look at the situation in 2010, you might have questioned the capacity of biodiversity science to rise to the challenge. We knew a tiny fraction of the multicellular organisms on our planet, and we had no real capacity to monitor biodiversity, track biodiversity in any sort of spatial sense. 2045, the PBM will be complete. We will have filled all of these dark taxa in, all life on our planet, all multicellular life will be registered, and the world will be looking like this. We will have biosurveillance networks scattered across it. Our work has been supported by a tremendous range of agencies here in Canada. I work with a spectacular group, many of whom you'll get a chance, some of whom you'll get a chance. There are about 100 people here that help make this possible. I'm so grateful to you joining either the board of directors or the SSC for this project, because the great thing about biodiversity sciences only can be done as a grand coalition. I'd hate to be an astronomer where you can just, you and your friends can build a telescope, and it needn't be international. And this is where we are today. And things are bubbling up in South Africa, as I mentioned. And I just look forward to a world that, as time marches over the next 20 years, it goes green. We're setting up this biosurveillance system around our planet and placing humanity in a position to better protect life. So that's my couple of minute long thing, too long thing, I think. But in any case, thank you.